in this video, I want to talk a little more about the Hilbert basis theorem. And in particular, I want to talk about the proof of this theorem given in Dummett and Foote. So just to recall, what does this theorem say? R is a commutative ring with an identity 1. If R is Noetherian, so is R bracket X. Okay, so why is this proof in Dummett and Foote different than the one that I gave you? The first thing I want to highlight is that at this point, Dummett and Foote do show in the proof that a PID is a UFD, they show that a PID satisfies the ascending chain condition on ideals. But they have not yet shown that any Noetherian ring satisfies the ascending chain condition on ideals. So they're not able to use that fact in their proof of the Hilbert basis theorem. But we did. In the first proof, we said, OK, let's take this ideal J generated by these leading coefficients of polynomials that we chose one at a time, A1, A2, A3, and so on. R is a Noetherian ring, so this ideal is finitely generated. And Dummett and Foote can use that fact as well. But then we said that there exists an M such that this ideal is equal to the ideal generated by the first M AIs that we picked up, A1 up through AM. And in the first video, I didn't really talk about that in detail, but why is that actually true? I mean, we know that there's some finite generating set, but how do we know that we can take that finite generating set to be the first M AIs that show up? Well, you can just consider this chain of ideals, each one contained in the next. The ideal generated by A1, the ideal generated by A1 and A2, the ideal generated by A1, A2, and A3, and so on. This ring is Noetherian, so this ideal has to terminate at some point, right? Like this chain of ideals has to, at some point, AM, they're equal for all of the ideals in the chain past that point. And that's the fact that we're using. So we have some point where this chain stabilizes. That means that AM plus 1 is in the ideal generated by A1 up through AM. So Dummett and Foote can't use this fact yet, right? Because they know that there is a finite generating set for this ideal, but in order to say that there's this finite generating set, A1 up through AM, the thing that we're using is that in this Noetherian ring, ideals, ascending chains of ideals have to stabilize. OK, so that's one difference here. All right, so how does the proof in Dummett and Foote go? Let's say I is an ideal in R bracket X. The idea is going to be to consider the set of all leading coefficients of polynomials in I, not the ideal generated by a sequence of chosen polynomials in I, but let's just take all the leading coefficients of all the polynomials in I. That is an ideal. And OK, I prefer the first proof that I gave of the Hilbert's basis theorem, but this is a cool fact, and I want to prove this anyway, even though we didn't need it in that first argument. OK, so how does this go? Well, 0 is a polynomial in the ideal. So it's sort of a convention. The leading coefficient of the polynomial 0 is 0. Right. OK, so now let's take two polynomials in the ideal. F of x, which is a times x to the d plus lower order things, x to the d minus 1, x to the d minus 2 times some coefficients. B is going to have leading term b times x to the e, two polynomials in I. What does that mean? A and b are in L. So for any r in the ring, let's consider the polynomial r times x to the e times f minus x to the d times g. OK, so what's the degree of this first thing? Well, if r is not 0, this is going to be x to the e times something of degree d. The lead coefficient should be r times a times x to the d plus e should be the leading term. And here we'll get b times x to the d plus e. OK, so what does that mean? Either r times a minus b is the leading coefficient of this polynomial. And in that case, r times a minus b would be in L, because clearly this is in I. OK, that's important enough that I'm going to write that. This is clearly an I. So either r times a minus b is a leading coefficient, and this is also in L, or maybe this isn't the leading coefficient. Why not? Because maybe it's 0, and the degree of this thing is not actually x to the d plus e, but it's smaller. Either way, what have we seen? Take r equals 1, and you've seen that for all a and b in L, a minus b is in L. And that's the subgroup criterion. That'll show that L is a subgroup of R. And it's closed under multiplication by R. If you just take b equals 0, if a is in L, then r times a is in L for all R in the ring. So that shows we're in a commutative ring. These facts together show that L is an ideal of R. Okay, so I'll pause and erase, and then I'll give you a pretty detailed sketch of the rest of the proof of Hilbert's basis theorem, the one that's given in Dummett and Foote, section 9.6. How does this argument in Dummett and Foote work? So we have this ideal I, and we've seen that if we take the set of all leading coefficients of polynomials in I, that forms an ideal L in R. And now, since R is Noetherian, L is finitely generated. So let's write down some finite generating set. L is the ideal generated by A1 up through AN. And the idea is for each one of these AIs, let's choose some polynomial in I with leading coefficient AI. So for each AI, let Fi be some polynomial in I with leading coefficient AI. Okay, let's now, each one of those polynomials has a degree, f1 up through fn, and let's take capital N to be the maximum of those degrees. And now, for each degree between 0 and n minus 1, we're going to take LD to be the set of leading coefficients of polynomials of degree d in I together with 0. And the same argument that we use to show that L is an ideal of R is going to show that LD is an ideal of R. So every one of these LDs, L0, L1 up to Ln minus 1, these are all finitely generated. So for each LD, we can choose a finite generating set. It's generated by BD1, BD2, up to BDND. This ND is just going to be the number of these generators. It's going to change depending on your choice of D. But for each one of these Ds, we have this ideal of R LD that has a generating set of elements of R and D of these things. Okay, and now just like up here, for each AI, we're going to pick this polynomial Fi in I with leading coefficient AI. Here, for each BDI, we're going to let FDI be some polynomial in I with degree D. Oh, sorry, I'm missing something important here. Some polynomial in I of degree D, with leading coefficient BDI. So these FDIs are going to be made up. We have FD1 up through FDND. It's going to be a collection of a bunch of polynomials in I of degree D, each with leading coefficient BDI. All right, so how are we going to see that I is finitely generated? We're going to write down a finite generating set for it. Just like in the first proof, once we had this finite generating set A1 up through AM of the ideal J, we just chose polynomials with those leading coefficients, F1 up through FM, and argued that I was equal to the ideal generated by F1 up through FM. We're doing something really similar here. So we're going to let I prime be the ideal generated by F1 up through Fn that we got here. And then together with FDI, all of these FDIs, where D is going to go between 0 and n minus 1. And for each choice of D, we have I going from 1 to ND. And now the claim is that this set of polynomials generates the whole ideal I. And how does the proof go? it's really similar to the proof from the first argument. So I will leave the details to you. You can look up the details in Dummett and Foote. But this idea is similar, but I think this argument's a little more complicated. For one thing, you're choosing a lot more polynomials. So I'll say more about what's going on here in the final video of this lecture.